fun and crazy spring break down at Daytona Beach? Huh? Fort Lauderdale? Get some sand out of your toes? And did anybody see the UNI game? The meltdown?
Oh, that was ugly.
That was impressive, I gotta say. All right, so don't mind what I say. Why don't you believe me?
Hit why?
Hit one.
Why? Why?
Do I not look like a hamster?
Type why? Keep hitting more.
This is my own code. All right, we'll do that some other time. We got issues to do here. So, I posted the updated version of the exam, and now it's time to actually go through clarifications of the exam. To those of you, I apologize to those of you who had nothing better to do over spring break, and so actually worked out the exam. I hope you do better next spring break. All right, so first and foremost, if you don't follow the format and put this stuff where it's supposed to be, I won't see it. Okay? Alles klar? Yeah, stimmt. Okay. Okay, begin each problem, not each part of each problem. That would make for a 3-volume set. Begin each problem on a new page. That makes my grading a whole lot easier. I get done with problem 1, I flip it to your next page, problem 2. Okay? All right, problem 1, the linearized lateral dynamics of transport airplane in straight level flight, altitude of 10,000 feet, 480 feet per second, are captured in part by the yaw rate rudder angle transfer function. It's a yaw rate rudder. What does that mean? What's yaw? Yaw? Yaw is, how does yaw differ from yaw rate? Excuse me? You mean it's the rate of yaw? Yeah. Ding, 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 you got it. All right, so there's the yaw rate, and the rudder is an angle. It's not a velocity, isn't it? Right? You guys know this better than I do, probably. So there's the transfer function. The units are degrees per second. That's the output. Because it's a rate of yaw, isn't it? Degrees per second. The input is the rudder angle, theta. So the units are degrees per second divided by seconds. Okay? Part A. First, find the poles and zeros of GP, the plant. Second, identify near cancellations. You'll know that when you do it. What is a pole zero cancellation? It's when the pole is almost identical to the zero. If you have s plus 1 in the numerator and you have s plus 1 in the denominator, you have a pole and a zero both at minus 1. But you can cancel those terms, can't you? So it's called a cancellation. All right, ignoring the poles in 2, obtain the time constants for all the poles as well as any zeta omega d information. Any questions on that? And again, it says solution. In my solution, I say C code 1A. Now, what you can do, if you want, is you can actually work in the MATLAB workspace, which I often don't like to do because I'm too prone to making mistakes. And then I have to rewrite all my code in the workspace, so I like generating a file and then correcting my file. But if you want, you can just say roots of a polynomial, and you can copy and paste. Right? But if you want to be different, then you can actually put your code in an appendix and give me the root command in the appendix in your code, and then I'll know where you got it from. If all you give me is poles and zeros and I have no idea where you got them from, I'm going to simply assume you got them from somebody sitting next to you. That's what it means by solution. Part B then, once you've got those, In relation to A, this is where there's the correction. I corrected it in my solution, but I did not correct it in the posted exam. In this blackout, this is what we call, what do they call this? Redact. A redact. This has been redacted. Yeah, the NSA got a hold of me and said, no, Sherman, you can't put that on the exam. No. So in relation to A, you should have observed 1, a near pole zero cancellation, and 2, that the tau associated with the complex poles is 2 times the tau associated with the remaining real pole. That's a little hint. If you don't get the taus right in part A, go back and think, well, maybe Sherman's wrong or maybe I'm wrong. But somebody's wrong here, and then bring it up in class if you think I'm wrong. All right, so this is the change. It had been by ignoring all 3, ignoring the pole zero cancellation and ignoring that third real pole. Well, when I originally did this, by throwing that third real pole away, I got an approximate second order system that didn't look anything like the third order or the fourth order, because it's a fourth order plan. Right? It's got S to the 4th in it. So I said, no, let's make this life easier for you guys. Let's not throw that third one away, so they actually do look similar. Otherwise, the questions become a lot more difficult to answer. So this was meant to be not as complicated as that. So, you've got a 3D approximation then, don't you? What is a 3D approximation? It's a three-dimensional or third order system. If you look at the transfer function of the plant, it's 4th order. But once you do a pole zero cancellation, it'll be 3rd order, right? So that's what I meant by 3D. It's kind of a jargon there. And you call that G under half, or whatever you want to call that. Now, note that when you do that cancellation, in order to get static gains to map, you're going to have to include a constant in G hat. So they have the same static gain. Otherwise, you're comparing apples and oranges. Okay? All right. So, just a little note on that. And then give me the impulse response. What's the difference between the impulse response and the step response? Cody? Absolutely. Yes. Everybody get that? Roughly. All of this is rough. No, not exact at all. Okay. Any questions there? All right. Part C then. First, overlay the Bode plots of GP and GP hat. They should look kind of similar, maybe, possibly. And then comment on the accuracy of the 3D. This again, that should have been corrected to 3 because the other one was corrected. Everywhere where you see 2, go to 3. Yes, thank you. And this will be posted. Hopefully, though, you don't get bent out of shape over this. It's a very minor little glitch. Then use the data cursor to estimate the minus 3 dB bandwidth. So if I don't see data cursor information in your plot, guess where I'm going to assume you got the bandwidth information from? Person next to you. All right. So there's the solution. See the code. The code gives the figure. Then comment on how they compare. And then give me the negative 3 dB bandwidth for each system. Of course, if the systems look identical, then you can say, since they're identical, they have the same bandwidth. It's possible they might look similar. Maybe. Kind of. Who knows? Well, I know, actually. I can't tell you. They'd kill me. All right. Part D. Compute the yaw rate that the pilot would expect to achieve with a given rudder deflection of 10 degrees.
Should that be figure 1C, not 1B?
Oh, Yes, thank you. You got this. This is 1B. See, I started this figure numbering just this semester, actually. I kind of like it this way, because then I don't have to change figures 1, 2, 3, 4, 5 if I add another figure in. I just go, so this should be 1C. Should have found that, Does everybody understand this thing? Would expect to achieve, when? In the steady state, of course. There's going to be transients, right? When you're flying a plane, you give the rudder a deflection, the plane is going to start to yaw, but then it's going to achieve a steady state yaw rate, as long as that rudder is deflected. So what rate would the pilot expect to achieve with a 10-degree rudder deflection? Okay? All right, and include your units. From C, you should have also found that the design negative 3 dB bandwidth for yaw rate control using pilot control. This is all pilot control. There's no feedback here, right? This is all the plan. All right, is quite low. Suppose the pilot were to wiggle the rudder stick back. No, the rudder stick back and forth at a frequency of 10 radians per second, which is about 1.5 hertz. So what you have now is you have someone that, they give it a 10-degree rudder angle, and you get a yaw rate, and then they go back and they're just kind of a little nervous maybe, a little jittery at the stick. Just very small oscillations. What's the rudder going to do if it hits that frequency, or what's the yaw rate going to do at that frequency of excitation? And you might be impressed. Okay. Compute the peak amplitude of the resulting yaw rate. Remember, this is a sinusoidal excitation. So the yaw rate, because it's a linear system, is going to be sinusoidal in the steady state. It's not going to be a constant in the steady state. The whole idea of frequency response functions. You give me a sine in at a given frequency, I'll tell you the sine out at that frequency, right? That's the whole fundamental basics of FRFs or Bode plots. Any questions with that one? And notice it's peak, not peak to peak. If peak and peak, we're on a boat. Peak said to peak. Any questions on problem 1? All right, then, let's go to problem 2. I spent a lot of time on this problem. I wanted something that would give you a better feel for steady state errors. And so I went to actually satellite tracking, and I got this PDF file called Zenith Estimation. And I'll tell you, some of these aero people, they really don't know what they're doing. I was going to show you the PDF file, but I decided just to work it all out myself, because it's all trig. So what you have is I'll draw the pictures here, because it's an interesting picture. Here's the Earth, curvature of the Earth, and you have a satellite here at point P, right? And your horizon is this. That's the horizon, correct? So then what you have is you have the center of the Earth, and you have a satellite, or you have, in this case, it happens to be an ICBM. It started being a satellite, but then those approximations in that PDF file I just mentioned are actually pretty good. So I wanted something that was a little closer to Earth, like only 50 kilometers away or something, and something of interest. So you have an ICBM coming over the pole, or around the pole or whatever. And at some theta naught, it hits the horizon. You can begin to see it, right? Okay? And so this is its arc relative to Earth's center. And you begin to see it here. And then as it, and this is an antenna, it's tracking it. So as it comes across here, you're going to track it up to peak. That's the whole basis of this. And it turns out that when you work through the math, whereas it being a constant for a satellite, angle omega is pretty much constant for a satellite. When you see a satellite way out in low Earth or low Earth orbit, and you see it on the horizon and it starts coming across, same speed, same angular speed. All right, but not for an ICBM. For the ICBM, this is the apparent degrees. What do I mean by the apparent degrees? Well, this is what at time 0. So at time 0, this thing is coming mainly in, correct? So it has a very low apparent, relative to point P, it has a very low angular velocity. That antenna can just pretty much stay where it is, maybe tweak a little bit up or down, but then as it gets overhead, it's going, right? So this is what the angular displacement of the antenna does over time. It starts with very low angular velocity, and so what you have here is you actually have a complicated input. This is the command input. You're trying to get the satellite to track that command, so to speak. Okay? So what happens here is you have essentially a ramp, don't you? At this point in time, at 50 seconds in, it's basically a ramp with that slope. So can you track a ramp? Well, sure I can. If I have a type 1 system, I can track a ramp with this much steady state error. So you can track that ramp with that much steady state error. Okay? Does everybody know what I'm talking about? What happens if you set the steady state error here, and you set your controller gains here, and you get a ramp over here? Well, its slope is huge. Right? And the slope of the input, remember, you have an input. The unit ramp is this. That's the unit ramp. So if I specify this much steady state error for a unit ramp, and you give me a ramp that's this, I'm going to have 100 times the steady state error. Because it scales. The whole system scales by the magnitude of the input scales to the output. Right? If you take a block diagram, G, and you put in F, you get Y. If you put in 100 F, you get 100 Y. Right? So what this is it's actually, this problem has to do with trying to approximate at any given point in time the ramp structure of this input. It's not a ramp structure, but for small periods of time on the order of 5 to 15, 20 seconds, except when you get up here, it's a ramp. So that's the idea, underlying idea behind here. First order of business is ignore the antenna. I give it there just for completeness, to show you that you are making an approximation with this problem. You're ignoring the dynamics of the antenna, okay? If it's a very rigid antenna, you don't have to worry about it, right? But if it's a flexible antenna that's, on light material and oscillating possibly as it moves, especially if it moves very fast. So ignore the antenna. Obtain the motor speed transfer function. This is not a speed transfer function. This is a position transfer function. It's degrees of angle on the motor shaft divided by volts. Now here, what I should have done in this block is I say it here. Note the feedback sensor and the command potentiometer are 1 volt per degree. So when you measure this thing back in, when you're measuring this, you're measuring it with volts. It's degrees, but you convert degrees to volts. And then when you put this input in, this reference or command input in, you want to put degrees in, but when you turn the dial or whatever, it's volts. So really what's coming into here physically is volts. And what's operating the controller is volts. And what's going out of the controller is volts. But because I wanted to make the problem easy, I said, just suppose it's 1 volt per degree. Then we can basically look at all of this as just degrees. But understand it really is volts. Okay? All right. Okay, so give me the motor transfer function in RPMs per volt. Let me see if you can convert units. Because this is how you'll buy the motor. When you buy a motor, motors are not positioning systems. They're not going to advertise you get 3 times 10 to the 50th degrees of position for a 5-second voltage application. They just say you get this much speed per volt. Right? So that's how you're going to spec the motor out, is with RPM or some kind of speed per volt specification. So that's part A. Any questions on that? Okay. Part B then, it's essential that the closed loop system be able to track the ICBM with a steady state error of less than 1 degree, roughly, for any point in time bigger than 2 seconds. Why do I say bigger than 2 seconds? Because when the thing first comes over the horizon, this is when you trigger the antenna to start tracking it. And there's going to be a startup transient for a couple seconds before it starts the steady state tracking of this thing. So don't worry about the first couple seconds. Okay. All right, now it sounds weird because this thing is actually time varying and we're talking about steady state error. Correct? Well, there is no steady state. But over short periods of time, this thing will actually go to a steady state, but that steady state is going to be changing with time. Okay? All right. There are no dynamics. When you say steady state, it doesn't mean everything is static. All it means is the transient dynamics are gone. So you're tracking something without those additional transients. All right. Consequently, it'll track a ramp with a slope which has, say, gamma with steady state error. I love that, steady state error. Yeah. I'm not even going to highlight that. In fact, I don't even think I'm going to change it. I kind of like that. With steady state error, that is gamma times that of a unit ramp. Okay. The command input shown in figure 1, up above, can be approximated locally at any point in time as a ramp having slope gamma. But gamma is a function of time. Clearly the slope in this figure 1, which I didn't even caption it figure 1, but you might be able to figure out what it is. Where's the slope the steepest? Or the largest? At the end. So you want to estimate the slope. All right, if you can track an input with this gamma slope with finite errors, then certainly you can track it with smaller gammas with better errors than that. Right? So the worst case scenario is up here when it's directly coming right overhead. You want to be able to track it with finite errors. So in this part, it's a very long description, but it sets the stage for the other stuff. Find the gamma value. All right, and it says solution. So if I see a number for gamma and I have no idea how you got that number, it came from a friend. Now, what's a very easy way to show me you know how to get a slope? Huh? What's a real straightforward way to get the slope toward the end?
2 points.
You're an algebra person, aren't you? I'm a geometry person. I'll just draw a line. You can take any 2 points and do it with algebra, can't you? But if I take, and again, I could use a ruler, but in my solution, since they have to be, formatted for you guys to read, I can't put a ruler in the PDF file. So I just insert a line here. And then from this line, I say, well, it's obvious what this is, and it's obvious what this is, and so that's what the slope is. So show me something that shows you know how to get a slope. So that's that one. This is where we get into the more current material, more hardcore. In this case, G sub D is G sub M, right? Use the root locus pole placement method to design a lead controller that will satisfy the following specs. First, it's going to cancel the motor pole at -1. I want you to do a pole zero cancellation. I want your controller to cancel that pole. We've done this. I mean, remember we had, if you have a motor which has a pole here and a pole here, right? What does the root locus for the closed loop do as a function of gain? It just goes like this. But if I put a 0 over here, then it does this. Doesn't it? Right? But if I put the 0 right here, what does it do? These are gone. So it does this. We've never looked at problems like this because they're kind of trivial for root locus applications, but now you're going to actually do it. You've got a lead controller, lead compensator, and you want to cancel that plant pole out at -1. That's one spec. You want to ensure that all closed loop poles have time constants less than or equal to 0.2 seconds, and if they're complex, they have to have damping ratios greater than 0.7. All right? And spec 3, you want a steady state error of less than 1 degree for gamma times t, where gamma is the maximum slope you found in the earlier part. Because if you can get that 1 degree bound for that gamma, you can be guaranteed that the satellite will track better than that for all lower slopes. Any questions on that? And since it's 15 points, you need to show me some work here. This is really kind of the brunt of the current material. Now, this is simply for your benefit. Notice that I'm not saying that you have to, there's nowhere in those specs that you have to give me a root locus. But since this is a root locus pole placement design method, maybe a little root locus might not be a bad idea to stick a plot there. So that's just for your benefit if you want. In order to validate at spec 3, plot the closed loop error response for the input in figure 1. The input in figure 1. Where's the input in figure 1? It's in, where is it? Come on, there it is. It's in the icbm.txt file. So that's going to be your U input for the LSIM, right? You've got a closed loop system now, not an open loop anymore. It's closed loop system, W, and you're going to want to run LSIMs with that input and see what you get. All right, and then comment. Does it validate? Is spec 3 the steady state error spec validated? And this is a feedback, this is direct feedback for you, because if you get to this point and you run LSIM with that input, and you get over 1 degree steady state error at that high rate of gamma, that high gamma slope, something went wrong. So you can go back and say, well, obviously I must have, either I used the open loop. That's the most common mistake people make, is they grab the open loop, but this is a feedback. It's closed loop feedback with a controller in there. So that's one mistake that might be occurring, is that you use the open instead of the closed. Another could be a simple numerical computation that, so you can go back and check and find out what you did. Might have been there. How'd that happen? You're supposed to be up here. There you go. I know how that happened. All right, problem 3. In this problem, we're going to look at the same problem as problem 2, but not from pole placement. Rather, we're going to look at it from a frequency domain investigation. Okay, so the first thing you want to do is suppose that the controller gain required to satisfy the steady state error spec is 1/30. Now, where did 1/30 come from, do you think? You think I just went up to one of those pizza gambling machines and got a ticket that said 1/30th? No, maybe 1/30th is reasonably close to what you should have gotten in problem 2. Maybe. But you don't need it, because I'm giving it to you. So, all right, the controller static gain. What's the static gain of this controller? What's the static gain of that controller? 0.6K. You let S equal 0, right? It's not K. But to get unity static gain, suppose that the K value that you need for required static gain is G of 0 is 1/30. So the controller static gain is required to be 1/30. Not unity. The controller gain is required to be 1/30. For a unity feedback control system with the open loop, G sub S is equal to K times G of the motor. Obtain the open loop Bode plot and use the data cursor to estimate gain and phase difference. Remember, the motor is given to you. It's 120 over S times S plus 1. That's just at the bottom. And now I'm telling you what K is. So all you need to do here is Bode K times G sub S. And do not use margin. Why? Why are you not allowed to use margin in this problem? What does margin do? It answers the question for you without you having to know anything except how to type margin. Which doesn't mean you know anything, it just means you can type better than I can. So I want you to use the data cursor. You're always welcome offline, all right, to verify what you got with the data cursor. But what it says here is estimate. So I don't expect you to get what margin is going to give. I'm expecting you to use a data cursor and get that thing in the right, that X thing in the right location, and then approximate things. And if you use margin, don't submit that information in your exam. You can just use it to see, did I get my estimate pretty good or not? Or was I off by orders of magnitude? Any questions on that? So in this picture, I expect to see data cursor information. Now, just because you have information doesn't mean that you can leave this blank. I'm not going to infer what your answers are by data cursor information. You still have to write your answers down, but they will come directly from the data cursor. Design a unity static gain lead compensator, all right, to give closed loop static gain of 60, or closed loop phase margin of 60 degrees. So you've got the K thing in there. K is 1/30. That becomes basically part of the plant now, doesn't it? You've integrated it into the plant. But now you're going to put an additional compensator, which is a unity static gain compensator. Why do I want unity static gain?
So you don't mess with the other stuff.
So I don't mess with that 1/30th, which was what I needed for my steady state error to be what it should be. Right? Because you're letting S go to 0 for steady state error. So if the additional compensator you include has unity static gain, when S goes to 0, it's 1, and it hasn't messed with your other specification. And again, this is another biggie. This is a 15-pointer. And there, for your convenience, you can insert a block diagram, or not a block diagram, you can insert a Bode plot that might actually help you in your development of the compensator. I strongly encourage you. I'm not saying you have to do it, but it's going to be really difficult to convince me to know what you're doing if you don't show me a Bode plot. All right, part C, closed loop Plot the closed loop error response to the ICBM input and comment. So it's the same thing. You have that text file, you use LSIM on your new. I called in my solution, I called the closed loop for problem 2, I called it W2. Closed loop for problem 3, I call it W3. And then I just overlay plots of W2 and W3 and for that LSIM and see how they do. So this is to see how it compares. Now this is not an overlay. There's no overlay on this one. There will be in the next part. This is basically to see, does this plot satisfy the steady state error response? Like the one in 2D did. Right? And it should. This is the part where you overlay the step responses of the two systems. The one that you use pole placement controller design with, and the one where you use frequency domain phase lead design with. And when you overlay them, you should see that there's a little bit of difference between them. Okay? And then comment on the most obvious difference between them. Any questions on that one? All right. Last one is a time delay problem. This problem addresses the problem I've talked about in class many times, is that you have a satellite, you want to transmit a signal from here across the world to here, but it's got to go through at least one satellite. In low Earth orbit, lots of satellites. It's called hopping. It hops across the satellite. So what you have here is you're going to address the importance of frequency response phase in the context of time delay. As I told you before, most mechanical engineering problems, they don't care about phase. But you guys in Aero have to care about phase immensely, because phase drops lead to instability, and you guys have time delays. So, communication satellite that links a controller center to a micro drone is shown at the right. Transmission delay time is delta. The delay is present in sending a signal to the drone. That delay is also present in receiving a signal from the drone. So how much delay do you have in your closed loop, in your open loop? In the forward loop, where you're sending it from the control center to the drone, there's a delay of delta. In the feedback loop, when you're measuring where the drone is and you're sending that information back to the controller, there's a delta. So how much delay is in the open loop? 2 delta, don't forget 2 delta. All right. A lead compensator designed to add phase margin to the system resulted in the following forward loop transfer functions. So you're not designing a compensator. This is the design compensator. All right, and this is the forward loop transfer function. The forward loop transfer function. It's got that delay in it. That's the transfer function for a delay. So there's the forward loop delay, but remember, you also have a feedback loop delay. Don't forget that in your open loop. That's really important. It's the open loop that you use to get the closed loop stability, isn't it? 1 plus GH equals 0, right? Remember that? It's not just 1 plus G. You can't ignore H if H isn't 1. So there's, and the feedback loop is H, so the open loop for the Bode plot for delta equals 0 is shown at right. And I'm giving you this information here. All right, because you've already done it in other problems. I'm not going to double jeopardize you. If you don't know how to get the information here, in the other problem, maybe this problem will help you go back and figure it out. But I'm not going to double penalize you and ask you to get it here as well, and it's not being really altruistic either. It makes my job a real pain in the butt to grade if you don't get it right. So there's a self-motive there. All right, so there it is, but that's for delta equals 0. Determine the maximum value of delta for which the closed loop will remain stable. I can say no more. This This is for delta equals 0. What happens to e to the minus s delta when delta is 0? It's gone. E to the 0 is 1. What happens to e to the minus s delta when delta is not 0? Well, it's there. But we're not in the s domain, we're in the frequency domain. So what does the e to the minus s delta become? E to the minus I omega delta. Oh, that's a unit phasor. Does nothing to the magnitude of the open loop, but adjusts the phase by negative omega delta. We went through this. Okay, so you need to find the maximum time delay such that the closed loop will remain stable. Part B, verify your answer by obtaining an open loop system, including time delays, Bode plot. So to do the open loop, including time delays, the simplest way to include time delays is to find the s variable. Right, there's two ways to compute a transfer function. Let's take 1 over ss plus 1. I can say, if I have this, there are two ways that I can define a transfer function for that thing in MATLAB. One is g equals tf 1, 1, 0. Right? That's via the coefficients of the polynomials. The other way is this way. And then g that way. This way for time delays is expedient. To get a time delay in here, whereas this way, you don't have polynomials anymore, so you can't do it. So this is how you would incorporate a delta second time delay. Now remember, that's for a delta second time delay in the forward loop, but you're looking at the open loop. So be careful with that. Draw the black diagram. You got a forward loop here, G. You have a feedback loop here, H. Right? What's the open loop? It's the whole thing. Because the closed loop is G over 1 plus GH. I'm doing this really sloppy because I'm not going to leave you by the hand at this point. I just want to sketch it out to trigger things in your memory that if they're not clear, you go back and you straighten it out. So the closed loop for this system is G over 1 plus GH, isn't it? So the crucial element for closed loop stability is not G, it's GH. It's the open loop. And there's an e to the minus s delta in here. And there's an e to the minus s delta in here. So be careful what, again, I'm trying to emphasize it so that I don't have to, because if you get it wrong in the first part, then it's going to ripple into getting it wrong in the second part, the third part, and then it makes migrating frustrating, and everything gets frustrated. All right. Okay. So what you're supposed to do here is verify. Obtain the open loop system, including time delay, and then use the data cursor to obtain a closed loop phase margin. What should the phase margin be for the maximum time delay? Verify your answer in A. You found that maximum delta. You're going to put that delta in. What does it mean that the phase becomes, the open loop phase becomes when delta's in? It becomes negative 180. Time delays cause closed loop instability by dropping the open loop phase. And if the open loop phase is minus 150 degrees, right? Then the closed loop phase margin is 30 degrees. You're 30 degrees above 180. Everything's fine. But if a time delay were to cause you to drop 30 degrees at that location where the gain crossover is, then at the gain crossover, which is 1, you have minus 180. You've just satisfied both of the root locus criteria, the magnitude and the angle criteria, which means that I omega is a root of the closed loop, which means the closed loop is marginally stable because you have a root on the imaginary axis. Remember, the whole idea of phasing gain margin gets back to the root locus, right? GH of S is -1. That's the same as 1 plus GH of S is 0. That means that S is a closed loop root, right? Closed loop root is value of S such that 1 plus GH is 0. Why? Well, because 1 plus GH is the denominator of the closed loop. And when the denominator is 0, that's called a closed loop pole. So you set 1 plus GH equal to -1. But that means you set 1 plus GH equal to 0 is the same as GH equals -1, is the same as GH is magnitude 1 with an angle of 180 degrees. This is root locus magnitude and angle criteria. So when you're in your frequency domain, it becomes 0 dB at the same frequency that your phase is -180. And if that happens at one frequency, that frequency is a closed loop pole. And it's not just any old closed loop pole, it's a pole on the imaginary axis, which means your system is marginally stable. So the last part of the exam is for you to do a little of your Google searches and investigate whether or not transmission latency would be a factor in LEO, MEO, or geosynchronous communication satellites. I've given you 2 references there that you can use. By the way, BTW, you are encouraged to copy-paste material that supports your conclusion, but don't make it a novel. So the idea here is you're going to use that information, or you're free to Google other information. But whatever information you use, give the source. If you copy and paste something, tell me which source it's from. Is it from 1, is it from 2, or is it from your own third source? But the idea here is that you're going to look a little bit and see what are delay times for low Earth orbits and for medium Earth orbits. And under which scenario would we not have to worry about this time delay that you measured, this maximum delay? All right, any questions on that? All right, see you guys on Wednesday.